Good afternoon, Professor.
Hello, guys. Nice to see you. Okay, I believe there will be not many people today on Friday, so I guess we may start, and if someone joins, that will be good. So last time we stopped with the discussion of reflectance of mechanical waves, which are, or some pulses, which are moving along the string, and one end is attached to some fixed support, like some wall, for instance. Okay, I guess we will continue from this point, just to refresh a bit, and give some general description of such effects as reflection at different conditions, and also transmittance of mechanical waves at the interface between two different strings. And then we will proceed with the calculation of rate of energy, which is moving through the string with some sinusoidal wave on it per unit time. So it will be some power, which is transmitted through the string. When we have some simple harmonic oscillator causing the disturbance and creates a sinusoidal wave which travels along this string. Okay, so let us go to another screen. And as I shortly mentioned at the end of last discussion, so let's consider some support. We have some pulse, which is moving to the right. Then when this pulse reaches the wall, let's go like this, it will exert certain force which is directed upwards on the wall, kind of pushing wall upwards. And according to the third law of motion, the wall will exert some force on the string, which is equal by magnitude, but different in direction, so it will be downwards. And this reaction of the support will result in the reflection of this pulse, but it will be an inverted pulse. It will be something like this. And it will move in opposite direction. So with this part is more clear now. So let us consider another option. So when we have also a string with some pulse moving along it, and it is fixed to some ring which can move, like slide up and down on some pipe. Then we don't have this condition that the this point where the string is fixed is firmly fixed to some support. So this support can move together with the end of the string. So what happens now when when this pulse reaches the end? We will see something like this. Let's say it will go to the maximum value. So this ring will go up to the maximum, to the amplitude of the pulse. And then the tension, backwards tension of the string will pull this ring backwards down. And this will generate the same pulse. So it will not be inverted anymore, which will move in opposite direction. So based on the conditions which the end of the string experiences in terms of how it fixed, we can have two different reflected pulses. It can be either inverted or not inverted. So let us consider a system of two ropes which are attached to each other, and ropes are different with different, we last time proposed such a parameter as mu, as linear density. So there are two ropes. One is, let's say they are made from the same materials, but one is thinner, another is thicker. So if we have some pulse which is moving along the thinner rope, like string, to this interface between where two kinds of strings are attached. And here we have a thicker one. Then we will have two effects actually. First of all, it will be reflection, what we already considered, but not all energy of the pulse, original pulse, will be reflected. Some will be, energy will be transmitted, and this will look as following. So we will have some reflected pulse, which is inverted in comparison to the original one. And then in this thicker string, we'll have a transmitted pulse. So the distance between reflected and transmitted pulses at a given time after this event of reflectance and transmittance happens will be different. Do you have an idea why these pulses will be at different positions with respect to this interface after the same interval of time? We were deriving equation for the velocity, like speed of wave motion along the string. And yeah,
maybe it is because, as you said at the beginning, they have different mu.
exactly. Like... Yeah, you are right. So the speed is equal to the square root of tension divided by mu. So if this larger, like thicker rope, obviously, if they are made from the same material, obviously the thicker one will have larger mu. So larger mu in denominator means smaller speed. And that's why this reflected wave will go further from the interface in the same interval of time as the transmitted wave. And what is also important to keep in mind, that amplitudes of these reflected and transmitted waves, they will be smaller than the amplitude of the original wave, because only part of wave energy or pulse energy is reflected and part is transmitted. So since amplitudes define the amount of energy it transmits, we will derive these equations just a bit later during this discussion. Then amplitude should reduce for reflected and transmitted waves. Okay, another option for, so we can write here that, let's say this is V1 speed of motion of this wave, speed of traveling, not motion, yeah, speed of traveling of the wave along the string, we denote as V1. So here it will be minus V1 because it goes in other direction, and here it will be V2. So there is another thing what you need to remember. If there is some pulse or mechanical wave which moves from the medium with higher speed of traveling of the wave to the medium, towards the medium with lower speed, like in this case, V1 is larger than V2, then we get inverted reflected pulse or wave. If we have opposite picture, let's say we have original pulse which moves through the thicker string, and it has some interface with the thinner one, then it will also experience some reflectance and transmittance. However, the reflected wave will be not inverted, so it will be actually the same. Here it will be also upwards, but I mean not very correctly drawn, because here should be larger distance, something like this. Yeah, so before it was moving with some V1, here is minus V1, and here's V2. But in this case, V1 is smaller than V2. That's why we don't get any inversion of the pulse of the reflected wave from the interface. So these conditions just keep in mind, because that could be relevant for certain conditions when you consider some cases or solve problems, because sometimes you need to take into account change in the phase of reflected wave, and depends from which side it's moving, from which environment it approaches the interface. It may change its phase, means be inverted, or may not change. So that is relevant to keep in mind. Okay, so once we have already defined this, and as you heard, we mentioned several times about this relationship between energy which is transmitted by wave and its amplitude. Definitely there is some relationship between these parameters, and we need to figure this out in a more quantitative way and get some equations for amount of energy which is traveling together with wave along the string. So in order to demonstrate that mechanical wave or pulse which travels along the string possess some energy, it's good to have such a simple example when, for instance, we have some pulse which moves to the right, and here we attach some body with mass m, and then it's fixed to some support. So when this pulse comes to the point where this mass is located, it will look something like this. So the mass will move upwards, means that it will increase its potential energy, and means that energy of the wave was converted in the potential energy, increase of the potential energy of this mass. So definitely this wave or pulse brings some certain amount of energy which can do some work. And now we want to quantify this. So we will consider a system with some simple harmonic oscillator, which is attached to a string, and we have some sinusoidal wave generated in the string. So along this discussion, we will consider some small element of this string with the length of dx and mass dm. And if we consider the motion of this small element in the, like along the axis y, it will move actually up and down. It doesn't change location along axis x. And this movement will be described, it will be some simple harmonic oscillation, or this movement of up and down, because this sinusoidal wave is generated by a single harmonic oscillator attached to its end. So each element of the wave in the y-axis will also move as a simple harmonic oscillator. And definitely it will possess some kinetic energy. So we know that kinetic energy is 1 over 2 mv squared. So since we have very small element of the string, we will deal with some delta A, small amount of kinetic energy, will be equal to 1 over 2 times dm times v squared. So let us first define what will be dm. dm is product of already mentioned linear density mu to the length of this element dx. So now we need to think about this speed. So as we mentioned, this element of the string will follow some simple harmonic motion. And for that, we derived the expression for the location, like y as a function of t, our previous discussions when we were discussing oscillations. And also, we can take the first derivative, dy over dt, to get the velocity, like speed, velocity of the simple harmonic oscillator. So that velocity can be calculated with this equation, minus omega a cosinus, cosinus kx minus omega t and plus some phi. Yeah, so we actually derived this equation when we were considering the vertical speed of elements of the string when we have some sinusoidal wave moving through it. So this is exactly what we need to calculate kinetic energy. So here we can assume that phi is equal to 0 for simplicity and substitute this equation instead of v for calculating the kinetic energy. So we will get dk is equal 1 over 2 times we can put, oh sorry, here I forgot to put dx. So this dx we will put at the end of expression. And here we will write mu times minus omega a cosinus kx minus omega t. And this is square. And here at the end, dx. Okay, so let us get this square. So it will be dk equal 1 over 2 mu minus will be gone. And we will have omega square a square cosinus square kx minus omega t dx. Okay, so now we have this equation and we want to get the kinetic energy which is located in one wavelength of this sinusoidal wave. So it's called k lambda. So in order to do that, actually what is transmitted through the, in other words, what is transmitted through the string with this sinusoidal wave traveling along it during the time interval which is equal to the period of this wave. For this purpose, we need to do some integration. 1 over 2 times mu times omega square a square. And then we need to integrate this cosinus square kx minus omega t dx from 0 to lambda. Since these parameters are independent on x, they are not under the integral and just considered as constants. Okay, so we have this integral. Let us write it again on the next slide, and we will proceed with the solution. K lambda is equal to 1 over 2 mu what was there, mu omega square a square integral from 0 to lambda cosinus square k x minus omega t dx. Okay, so in order to have, since we don't have time involved here, and it actually doesn't matter at which time we do this calculations, let us consider that we do it at t equals 0. Then we get rid of this constant, so it will be easier to deal with this integral. So that will be equal to 1 over 2 mu omega square a square integral from 0 to lambda cosinus square kx dx. Okay, so now how do we take this integral? It's not so straightforward as just integral of cosinus, because we have this square. So what we do for this, we need to find some substitution of k cosinus square kx, and according to trigonometry, we can write something like this: cosinus square kx is equal to 1 plus cosinus 2kx divided by 2. So if we substitute now cosinus square kx with this, we will get two integrals, but then it's easy to deal with them. So let's continue. We have 1 over 2 mu omega square a square, and here we have integral from 0 to lambda 1 over 2 dx is this part, and then plus 1 over 2 integral from 0 to lambda cosinus 2kx dx. So we can proceed with the first integral, but in order to take the second integral, we need to multiply and divide by 2k in order to have in this under the sign of differential instead of x, k, like 2kx. Then we have the same independent variable 2kx and d2kx. And this is possible because it's constant. If we multiply this x with a constant, it will not change anything because the derivative of the constant is 0. So it will not change anything. And that's why in order to have the final form of these two integrals, square a square, this one we can already write that it will be x from 0 to lambda divided by 2 plus 1 divided by 4k, because we multiply and divide by 2k, integral of 0 to lambda cosinus 2kx d 2kx. Okay. Now we finally can get this integral a square. This will be lambda divided by 2 plus 1 over 4k. Then this integral will be sinus 2k x 2k, oh, sorry, sinus 2kx from 0 to lambda. Okay, let us think what it will be. So obviously sinus 0 will be 0. So we don't care about this part. But what will be sinus 2k lambda when we take this limit? We know that from previous discussion, let's write it here, that k is equal to 2 pi divided by lambda. So this is wave number, angular wave number. We introduced this parameter of the wave previously. Now if we consider 2k times lambda, it will be 4 pi. And sinus of n pi, when n is equal to 1, 2, 3, 4, and so on, will be equal to 0. So actually this integral in this limits from 0 to lambda will be equal to 0. And eventually we will get, let's write it on the, let's write it here and then we will rewrite it. So it will be 1 over 2 mu omega square times a square times lambda divided by 2. So now we can rewrite this part on the new slide, assuming that we have 2 times 2 in the denominator, so it will be 1 over 4. Will be kinetic energy, which is of a sinusoidal wave in the interval of 1 wavelength, will be equal to 1/4 of the product mu times omega square times a square times lambda. So this part is done. We calculated, like derived the equation which describes kinetic energy accumulated in this 1 wavelength of a sinusoidal wave on which travels along the string. So similar process can be done for the potential energy which is accumulated in the in 1 wavelength, so it will be a bit more complicated, so we will not consider detailed derivation, but what is necessary to know that potential energy accumulated in this 1 single wavelength, it will be exactly the same equation. It will be 1/4 mu omega square a square times lambda. So now when we have expressions for kinetic and potential energy, we can calculate the total energy, which will be just twice of this equation. So total mechanical energy, which is accumulated in the single wavelengths of sinusoidal wave, mechanical sinusoidal wave, will be equal to 1/2. I mean, probably better to write like this, will be equal to the sum of kinetic energy and potential energy per 1 wavelength, and this is equal to 1/2 mu omega square a square times lambda. Okay, so this is the expression for the total energy per 1 wavelength, so don't forget it. Now we are interested in the question, we also mentioned this before, how much energy is transmitted through the, like each element of the string per unit time. So it's kind of rate of energy or power which is distributed along the, like spread along the string. So by definition, we know that wave is traveling along 1 wavelength during time interval which is equal to the period of this wavelength. So that's why all this energy E lambda, which is accumulated in along 1 wavelength of the wave, will be transmitted through each element of the string per time interval which is equal to 1 period. So taking this into account, the power P, which by the way, power, who knows what will be the units for power?
Watts.
Uh,
Or joules per seconds, or
yeah,
what's
you're right. So to be more precise, it's joule per seconds. So it's amount of energy which is measured by which is defined by this E lambda, uh, transmitted through the string per unit time per second. So in this case, P is equal to E lambda divided by T, because all of this energy, E lambda, transmitted through each element of the string in time interval, which is equal to the period of the wave. So that could be written as 1 over 2 times mu omega square A square lambda divided by T. And what do you think is this? Lambda divided by T. What
velocity?
velocity? Yeah, it's speed v. So final expression will be p 1 divided by 2 mu omega square a square times v. So this is equation for power, which is transmitted through the string when some sinusoidal wave is traveling along it. So what is important here that this power increases linearly with the speed of wave propagation through the string, and it increases as second power of angular, like of omega, and amplitude, like frequency and amplitude value of this oscillation. What is important to know that this particular case we considered so far only for mechanical wave, which is moving along the, traveling along the string, but it is actually true for any types of oscillations and waves, that their power, which is transmitted by these waves, is proportional to the second power of frequency and second power of amplitude. So if we take, for example, sound waves, which we will consider in more details in the near future, that corresponds to frequency of the sound wave, and amplitude is the maximum value, maximum and minimum value of pressure in air, which sound wave creates. If we also can, so it's also kind of, it's mechanical wave. It's just longitudinal wave, different from the transverse wave, which is wave along the string. But it follows the same concept. It also proportional to the power it transmits is proportional to square of the frequency and amplitude. Moreover, this rule also is valid for electromagnetic waves, which are completely of different nature, but they are also caused by some harmonic, simple harmonic oscillator. They are sinusoidal waves of connected, like related to each other, changes of electrostatic and magnetic fields. So electromagnetic waves, they also, the power actually will be light intensity if we are talking about some visible electromagnetic waves in the visible range. So this light intensity will be proportional to the square of frequency and square of amplitude values of electrostatic field or magnetic field in this electromagnetic waves. So that's why deriving these expressions for the string, we can translate this concept for a very broad spectrum of different types of waves, which is kind of interesting how things are related. And that happens because all of these types of waves have sinusoidal nature. They change according to sinusoidal, change the parameters which they are defined by according to sinusoidal law. Okay, so I guess we already discussed the most important topics of waves as much as we had time for during this week. I would strongly recommend you again to spend time reading the textbook and also consider the interaction, like interference effects, interaction between incident and reflected waves. That's another important topic which is definitely related to this subject of waves, and we unfortunately don't have enough time to discuss all these questions, but that is important, and please pay attention on this in the textbook to have more general picture about interaction between waves. That is another interesting and important topic. So next week, I think according to our plan, we will start working with sound. And if I'm not mistaken, that's probably the last topic in the framework of classical mechanics. So then after sound, we will move to molecular and thermodynamic physics. Okay, so if you have any questions, you are welcome. If not, I wish you good evening and good weekend. Take care and don't get corona and other diseases.
Thank you, Professor. You too.
Yeah, thank
Bye.
you. Bye. Have a good evening.